This is a review of class on May 7th, 2020. I thought we started by just kind of reviewing the equilibrium unit. So things we've talked about in the equilibrium unit include, we started number one, we started with rates of reaction. We talked about factors that affected rates, and they included such things as nature of reactant. So more complicated ones take longer to react. Surface area. We also talked about concentration. And my hand's kind of distracting over there, so we'll do this. Concentration, temperature, and the last thing was catalysts. Of those, we said that the most important factor, the one that we're dealing with the most, is concentration. That the concentration is what we're actually varying in all these equilibrium problems. Now, the second thing we did in this unit was talk about what is equilibrium. And we said it was an equal rate of exchange. So equal rate of exchange. The forward reaction and the reverse reaction must be going at the same rate. And the third thing we did was calculations. So last week on Friday, which would have been, I guess, May 1st, what we did on Friday was we did two different kinds of calculations. So we did find KEQ given equilibrium concentrations. And then the second thing we did was find equilibrium concentration given KEQ and some equilibrium concentrations. We had to find the unknown. Okay, then the fourth thing we did in this unit, this was on Monday, we worked on Le Chatelier's principle. It says that systems will stay at equilibrium if they're at equilibrium. So I'll say systems at equilibrium will stay at equilibrium forever until there is a stress. And we said that systems will shift their equilibrium to relieve the stress. The shortcuts were equilibrium shifts away from an increase and equilibrium shifts toward a decrease. So if you increase something, the equilibrium will shift in the opposite direction. If you decrease something, the equilibrium will shift toward what you're decreasing. That applies to everything except for pressure. For pressure, increasing pressure causes a shift to the side with less moles of gas. So if you're doing a chemical equation, increasing pressure will cause a shift to the side with less moles of gas, and decreasing pressure will do the opposite. Okay, so increasing pressure causes a shift to the side with less moles of gas. Decreasing pressure shifts to the side with more moles of the gas. Then on yesterday, which was May 6th, what we did, number 5, is we did calculations where we were given initial concentrations. That's not the equilibrium concentrations. So that required us to express the amount that reacted in terms of x. Sometimes to solve for x, you sometimes need a quadratic equation to solve for x. All right, so that's what we've done so far. And that's a review. And now we're going to learn something new today. So today we're going to do 2 new things. First thing we're going to do is calculations again. We're going to solve for K using initial concentrations like we did yesterday and 1 equilibrium concentration. And the second thing we're going to do today is compare reaction quotient to K to determine which direction reactions will proceed on the way to equilibrium. All right, so I tried to type that, probably was kind of noisy. I thought that would slow me down and let you think about what I'm talking about. So those are the things that are in the equilibrium unit. And we're finished with this. We're finished with the beginning concepts in equilibrium. And we will move into acids and apply some of these concepts. But we're really finished with the equilibrium unit. At least all we're going to do this year. All right, so now let's move into these kind of problems. We're going to calculate K, solve for K using initial concentrations and 1 equilibrium concentration. So now let's pull that out of the way, get back on my web camera, which really is just a phone using web IP in case you're interested in that. And here we go. So in this question we're given, let's get a new problem so we can solve it. Okay, we have CH3OH, and that's in equilibrium with carbon monoxide and hydrogen. To make that equation balance, you have to put a 2 in front of the hydrogen. In this problem, you notice that we're given an initial and an equilibrium concentration. The initial concentration of the CH3OH is 0.0740. I'm going to put I for initial. We don't have any of the CO. Notice it says 0 for both the CO and for the hydrogen. Now we know that there's going to be a change, and the change would be that some of this is going to react. So this would be minus some amount. We know that we're going to get some amount of the things on this side produced, and we don't know how much, but we do know that relative to whatever reacted over here, since there is a 1-to-1 mole ratio, that's going to be X. And a 2-to-1 mole ratio will mean this is 2X. All right, so we're going to go down by X amount, we're going to go up by X amount, we're going to go up by 2X because of the 2-to-1 ratio. So whatever reacts, we're going to get twice as much of the other thing produced. All right, at equilibrium, we would normally say 0.074 minus X because we started with that, X amount reacts. We started with nothing, we made X amount. We started with nothing, we made 2X amount. Now what makes this problem different is the pink number that I'm about to write. They give us the equilibrium concentration of the CH3OH. See the 0.0548? So we know that this is 0.0548 at equilibrium. So what that means is 0.074 minus x is equal to 0.0548. So now we can solve for x. All right, so if we do that, we would add x to both sides, subtract 0.0548 from both sides. So you end up with 0.074 minus 0.0548 equals 0.0192. So x is equal to 0.0192. Well, since we defined the CO as x, that's 0.0192. And that's 2x. So 2 times 0.0192 is 0.0384. So those are the equilibrium concentrations. This problem asks us to solve for K. So we know that K, the KEQ, is equal to the concentration of the CO multiplied by the concentration of the hydrogen squared divided by the concentration of the CH3OH. So now I plug in, the CO is going to be 0.0192. The H2 is going to be 0.0384. That has to be squared. Divide by 0.0548 that we were given. And we get our final answer, so 0.0192 times 0.0384 quantity squared, then divide by 0.0548. My answer should be 5.16 times 10 to the negative fourth. And just to make sure that I'm going to punch my number in correctly, I'm going to change this to this format so that I can type it in easily. I'm not sure what the person who created this quiz expects for a number. So we would say 0.000516. And we check our answer, and we see that it's correct. All right, let's do one more. Then I'm going to stop this little video. All right, let's just scroll through. Now this one might be interesting, so we'll try this one. All right, so what we're given here, we got 2 CO2 plus N2 equals 2 CO plus 2 NO. All right, so initially we have 0.290 of the CO2. And we have 0.190 of the N2. For the CO, we don't have any. And for the NO, we don't have any. Those are our initial concentrations, so we'll call that I. Now we know it's going to change. At this point, you know that this is going to change by some amount. You can call it X, but some of you might say, well, there's a 2 here, let's call it 2X, but I'm just going to call it X. So I'm going to say it's going to go down by X amount. Now we do know that if this X amount of this reacts, whatever reacts, since there is a 1 to 2 ratio, there will be half as much of this. So instead of calling this X, we would call this 1/2 of X, which is 0.5X. Now on the other side, X amount reacts, and there's a 2 to 2 ratio, so on the other side, we're going to have X amount of the CO, and you'll also have X amount of the NO because it's also a 2 to 2 ratio, and we said that X amount reacts. We don't know how much, but we know that some amount reacts, we called it X. We know that if 4 moles of this reacted, then you would have 2 moles of that. So if X moles of this reacts, you're going to have half as much of that, so that's half X. Now some of you might say, well, let's just call this 2X. And then if that was the case, you'd call that X, and you'd call that 2X, and you'd call this 2X. So you just maintain the ratios. All right, so we won't do that this time, but you could do that. All right, and then at equilibrium, we know that we would have had 0.29 minus however much reacts. We would have 0.19 minus 0.5x because that's how much reacted. And on this side, we would just have 0 plus x, which is x, and 0 plus x, which is x. Now, what else are we given in the problem? We're given that the equilibrium concentration of the NO is 0.0444. So we know that this is 0.0444, which means that x is 0.0444. So we also then know the equilibrium concentration of the CO because it's also x, 0.0444. On the other side, we have 0.29 minus x, but x is 0.0444. So 0.29 minus 0.0444 equals 0.2456. And then the 0.19, subtract, you did take away half of x. So instead of 0.0444, it's going to be minus 0.0222. So you get 1.1678, and that's our value for the nitrogen. So now we're ready to do the math. We know that Kc, the equilibrium constant in terms of concentration, is equal to the concentration of the CO squared multiplied by the concentration of the NO squared divided by the CO2 concentration, and that would be squared, and the N2 concentration, which is not squared. Now, we're ready to plug in the numbers. We have, for the CO, it's 0.0444, and that is squared. For the NO, 0.0444 squared. Once again, those are coming from right there. Divided by the CO, 0.2456. And that one was squared right there. And the last number, 0.1678. All right, so now we're going to go 0.0444 squared times 0.0444 squared equals, and then we're going to divide by the two numbers on the bottom, 0.2456 squared, and then divide again by 0.1678 equals. So now we get 3.84 times 10 to the negative fourth, which is 0.000384. So that would be our equilibrium constant, so we type that in, 0.0000384. All right, check answer, and it's correct. All right, so that's how you do this type of problem. And once again, what did I call this kind of problem? Solve for K using initial concentrations and one equilibrium concentration.